Yes, hello. So today I will present indeed a work about open-ended library learning in unsupervised program synthesis. So one motivation of this work, which is very familiar to the ALIFE community, is the open-endedness, so the quality of process which keep producing an increasingly diverse and complex array of artifacts or behavior. So for instance, in evolutionary processes with life forms, and it's also known that typically AI algorithms don't have this quality, but recently some researchers, some new work have tried to, with the belief that accumulating diverse stepping stones towards different direction may be crucial sometimes to tackle more complex question and challenge. So there is a bunch of work around quality diversity algorithm as it has been presented previously. So here in the representation, for instance, there is map elite, and it usually keeps an archive of solution across several dimensions. So it both have a performing quality criteria, but also a diversity criteria. The second motivation of this work is also the predominance of compositionality across both knowledge formation and also innovation. So the ability to reuse, combine, and transfer previous knowledge is both crucial to human learning and to adaptation, and it seems also crucial for open-ended innovation. So it could be, although it's always, of course, simplified representation, but it could be from genomics to soccer playing or to the invention of the internet. So now the question of how to harness this compositionality, which representation we could use, and programs, for instance, have a lot of compelling quality and are compositional, robust, expressive, and to a certain extent interpretable. And when they are paired with library learning, which means like the fact of saving certain program and be able to reuse them in a later step, then it could also enable to preserve regularity in a more potent way and to help this compositionality and transfer. So also in program synthesis, usually when there is library learning, it's commonly guided by neural search because of the combinatorial nature of the search space, which is exploding. So there is often a neural network which help searching through the space of solution that is learned. And one famous example of neurosymbolic algorithm is Dreamcoder that you may know. And on this work, this work built upon Dreamcoder, so I will mention a few things about it. So Dreamcoder learns a hierarchical library of building blocks represented as program, but it also learned the intuition of how to compose this building block, so via a neural network, as I mentioned. So it is quite a versatile system, and it has been applied to multiple domains. So from more classic program inductive tasks like physical law regression to also more creative tasks like logo generation. And it's also adopt a Bayesian framework. So in this sense, you can see the library as encoding a prior on program as it's learning a language, and the neural model aims to approximate a Bayesian posterior. So in that context, our question for this work was like, could such a neurosymbolic model growing a hierarchical library of program be leveraged for open-ended program discovery? So the first prototype we present today is like open-ended Dreamer. It aims to learn a hierarchical library of diversity-enabling program useful across niche. So the first change compared to Dreamcoder is that it doesn't need to require endless unpick task, and it adopts like a quality diversity framework. So as some previous talk, as I've mentioned here, you have represented certain niche across the behavioral space, which is cut. And in each niche, we want to find the most efficient, but also still novel solution. So here you see is represented the iterative loop of learning of open-ended Dreamer. So there is a first step of neurally guided program generation, where OED will like generate through both enumeration, maximizing the Bayesian posterior, but also through sampling, will enumerate certain program. The program will be split across niche as it's represented, and then there would be a step of novelty selection where the program are compared across the saved program in the archive. And then there is a step of abstraction. So this step is first refactoring all the program to write in equivalent form. and then it's compressing them and trying to abstract some, to find regularity shared between them, and then to grow like that the library. And finally, there is a step of training the neural network, which is used in the generation step, both on replace, so on elite program, but also on sample program. So yes, just to mention about this Bayesian posterior, I talk about. So here you can decompose it, I mean, to a factor into two terms. So the first one is a likelihood, is like how a program will fit in a certain niche. So Rho is a program and Z denotes a niche. And the second term, the prior, will denote how likely is a program in the library. So just, I won't mention exactly the compression algorithm, but I will just highlight something important. It's like, so when you have the elite program, so here they are split into bins. So every program can be after rendered as a structure, which is here represented. And when we abstract, we try to find regularity between some of these elite programs. So it's common substring, for instance, of subsyntactic tree in the representation. And then we abstract it, and the abstracted program is also a program, but it's a function of several arguments. So in that way, it's enabled to preserve regularity in a more potent and compressed way. We don't have to save all the instantiation of the program in the library, but we only save a function, like the function generating a few of them. So the model, I mean, as a first test bed, we experimented with the tower domain, the tower domain, which is also one of the domain where that Dreamcoder was using. And so here you see, for instance, represented different structure programs learn in different experiments through time, and I will come back to some of them. So here just you again see through time elements in the library. So every box is a library element, so it's a function, as I mentioned, so it's instantiated on different arguments. So again, for two different experiments that I will mention in a minute. And this is just to give you an illustration of the compositional and hierarchical aspect of the library. So this is a snapshot of the library at a certain generation. So you see that here we reuse previous program function in like later stage of the evolution. The orange one are the latest abstracted program invented in that generation. And yes, so you see how knowledge is reused. So we have a few, we run a few experiments. We run both ablation experiment, bias experiment, and also experiment around the novelty efficiency trade-off that I will go through. So in the ablation experiment, so we both have with ablation of the recognition model, with ablation of the novelty selection, and with ablation of the library. And in short, what we can see from those first experiments is that the recognition model, as you see in the green curve, is really crucial for discovering program. Notably, yeah, it's important to keep producing novel program. The library itself is important mostly to keep this sustained generation, but it doesn't necessarily have a strong advantage sometimes in terms of final diversity, because learning a library, and this I will come back in a later experiment, is also learning a language bias. So yes. And now we were also interested to wonder if how to experiment with inductive bias to guide the learning of symbol and library. So notably because it's common in like social natural system to have a lot of constraint and bias, social cultural bias, so guiding this the formation of innovation. So we both experiment with bias metrics. Also, in the CNN case, we use a pre-trained CNN as a distance for novelty evaluation. We also experiment with a bootstrap library. So we seeded the library with those elements which are indicated in the bottom left corner to bootstrap evolution. And lastly, we have an environment with stronger environmental pressure gravity-aware environment. And with box 2D, so here are some results about those experiments. So the experiment with the bias matrix and also the Bootstrap library seems to help also qualitatively to have some more compelling program in the invented and learned. And the physics, but also I mentioned the library also helped mostly to give a kick at the beginning, but in terms of diversity, it also sometimes it makes the diversity sometimes slow down because it becomes more biased also towards certain structure. And then the physics-aware environment is slowing down a lot and constraining, as we expected, the search space, which makes more consistent structure, but also a slower generation. So, and a point which is important on the system is that there is a lot of different pressure at play, both environmental efficiency and novelty pressure, and some of them are conflictive. So in here, what I mean by environmental pressure is, for instance, the ecosystem minimal criteria, the fact of the likelihood of a program belonging to the niche. The efficiency pressure here is enacted by a language bias. So it's we want to invent programs which are well compressed by the library. And the novelty pressure is the novelty selection which happen at the later step. So those two, learning a language, as I mentioned before, is also implies learning a strong inductive bias in the search space, which also may impede diversity. So we also observed that stronger efficiency and environmental pressure led to phenomenon of convergent evolution. And finally, a last point about this, there is a way in the system to adjust the exploration and to adjust this balance between novelty and efficiency to a certain extent. But when we have like too low efficiency or environmental pressure and want to push the novelty pressure, the compression algorithm may have a hard time because of finding regularity to abstract away. So that's still a delicate balance which could actually be automated also and learn. So in conclusion, Open-Ended Dreamer is a diversity-oriented search with a neurally guided library learning. It could be a promising direction for open-endedness. It can, because of saving in the library function instead of saving all the instantiation, it can preserve regularity in a more potent and versatile way. We also saw that we can guide the development of innovation using innate priors, bias metric, or also environmental constraint. And lastly, promoting greater exploration is crucial to offset the bias, as I mentioned, but induced by the growing language, and foster more creative divergence, but this balance is still delicate to maintain. So further experiment is needed. Also, we need to experiment with longer timescale to evaluate open-endedness effectively. Also with richer environment to have more like functional objective or like bottom-up objective. And another thing we need to evaluate in downstream tasks to evaluate the benefit of this novelty exploration in the first steps in other tasks. So yeah, thank you for any question.